Now I'm right. I'm right now.
Yes, please. So Mo Jia Li from Suzhou University from China. Yeah, and the talk is geometrical properties of degenerations of curves and surfaces. Please.
Yes. Good morning, everybody. I would like to begin my talk by thanking the organizers for inviting me to take part in this conference. Today's topic is the geometric properties of degenerations of curves and surface. My name is Mo Jia Li. I come from Suzhou University in China. Next, an important contribution to this report is from Washington, and he was also born in Odessa. You can see this picture is Washington. Since this year is Washington's 85th birthday, since these reports of mine can be used in his memory. I should like to give this talk in 3 parts. The first deals with background, the second part concerns degenerations, and then the last part related to open question. Let X be an algebraic variety. We are interested in the properties of the following 3 aspects. They are geometric, arithmetic, and algebraic properties, respectively. As the picture shows, the properties of these 3 aspects are closely related. You can see this. We pay attention to the relations between them. Now, let me give you 3 examples. First, example 1. A smooth algebraic surface X belongs to P3. If we have degree X is equal to 1, then X has infinite lines. If we have degree X is equal to 2, then X has infinite lines. But if we have degree X is equal to 3, then X has 27 lines. This conclusion was proved by Kelly Shermer in 1849. The following graph can better intuitively see the existence of 27 lines. You can see this and this. You can find the algebraic properties of X on the left, this, and its geometric properties on the right. This example shows the connection between these 2 properties. Next, let's look at the second example. Example 2. As we all know, this is a well-known result. That is a smooth algebraic curve over Q if its genus is G and G is greater than or equal to 2. There are finite Q points in it. This result was proved by Martins in 1985. This example shows that geometric properties determine arithmetic properties. Related to this example is the following result. This result was proved by Wells in 1995. That is, xn at yn is equal to zn, where n is greater than or equal to 3. This equation has no trivial integer solution. These are their pictures, Martins and Wells. I think they are very handsome. Now, let's look at the last example. This is watershed conjecture made by Bogomolov in 1983. If Y is a surface of genotype with tau is equal to this formula is greater than 0, then fundamental group pi 1 is not equal to 0. Although There are many examples to show that this conclusion may be correct, but it is a pity that in 1987, Moshton and Taiher used the Breadth group technology to give a counterexample. These are their pictures, Moshton and Taiher. Well, that's about it for this part. Right, now I'd like to move on to the second part, degenerations of algebraic varieties. Here is this definition. Let D be the unique disk and X, Y be algebraic varieties. We see that X is a projective degeneration of Y. If there exists a flat family pi, where pi is M into D, where M belongs to D product Cpn, n is greater than or equal to 3. M is a closed subscheme and satisfies 3 conditions as follows. 1. Pi inverse 0 is isomorphic X. 2. There exists 0 is not equal to P0 belong to D, such that pi inverse P0 is isomorphic to Y. 3. The family M minus pi inverse 0 into D minus 0 is smooth. Maybe you think the above definition is a bit complicated. This can be briefly said. Let Ft be a family of algebraic variety depend on parameter t, except t is equal to 0 and Ft is a smooth algebraic variety. Then we can consider Ft as a degeneration of F0. This leads me to my next point. That is the degenerations of curves. We pay attention to cubic pencil. Let F at Tg is equal to 0. Define a cubic pencil. Then by blow up, we get an elliptic fibration over P1. We have F S into P1. It means a morphism between S and P1. Moreover, every F inverse P is connected for NP belong P1. This is Kodaya. He classified the elliptic fiber in 1960. In fact, an elliptic fibration F over P1 can be considered as an elliptic curve E over CT. We all know section of F 1-to-1 CT points over E. Now, we assume that F has a 0 section. Since the integral section is very important, so we give its definition. It is disjoint from the 0 section. Here, in particular, here is a remark. In our case, there are only finitely many integral sections. Here's what I want to accomplish. My purpose is that, first, by studying the general position of the base points of the cubic pencils, we calculate the number of integral sections in fibrations of the surface. Second, as an application, we study the number of -1 curves on the above surface, so as to generalize example 1. This is very important. Finally, we give some relations between geometric, algebraic, and arithmetic properties of curves. In the section about degenerations of curves, here are my new results and new proof method in 2022. This is new result. Given n points in general position in P2, we classify the cubic pencil by base points. Our results are as follows. S like this equation. A cubic pencil is a cubic pencil with n simple base points. N is equal to 8, 7, 6, 5. Then the Mordell group EK of the fibrations are isomorphic to types respectively. You can see that if the Mordell group of the fibration is E8, the fibration is isomorphic to one of these two equations. You can observe that these are similar results. Dual of E7, dual of E6, dual of D5. Below, I will briefly describe this proof outline. The sketch or proof the steps as follows. First, given n points in general position in P2, we take 7 points in general position as an example. Then we get this result. About this result was proved in our paper. 2. In the corresponding fibration, we contract the appropriate -1 curves to obtain the corresponding spatial pencil. You can see this picture. We need first contract this -1 curve, P bind, and after contract different minus curves. For example, P0, P1, and so on. To obtain the corresponding spatial pencils. Finally, by isomorphic mapping between curves, the above spatial pencil, this, is transformed into a planar pencil. This is my new proof, that is, the pencil surface X is either P1 product P1 or the below up or P2 in n points in general position. The degree D of X is defined to be D is equal to 9 minus M. As an application, we give a new proof of the number of -1 curves in the pencil surface. Remarkably, this is a new proof, not a new result. Here is a remark to pay attention. The pencil surface of degree 3 is a cubic pencil in P3. Then there is a following theorem. The number of -1 curves in the pencil surface of degree 1, 2, 3, 4 is 240, 56, 27, and 16. I will also briefly describe this proof outline. First, contract an appropriate cubic pencil to obtain the corresponding elliptic fibration by blow-up base points. 2. Contract -1 curves to get a diapason surface and find the relations between -1 curves of the diapason surface and integral sections of the original elliptic fibration. Finally, the number of -1 curves of the diapason surface can be obtained by the number of integral sections of the original elliptic fibration. So we notice the integral section. This definition is very important. After talking about degenerations of curves, let us discuss degenerations of surface. This picture is Galois. First, let's look at a definition related to him. The Galois closure of a spirable field extension F over E is a minimal Gauss extension over E containing F. In fact, it is unique up to isomorphism over E. In order to better understand one of the theorems below, I give some basic knowledge. Let X be an algebraic surface of degree n in projective space. One can consider it as a branched cover of the projective plane CP2 with respect to a generic projection F, where F is X into CP2. The branch curve S is an irreducible cusp plane curve of even degree. S admits only nodes and ordinary cusps at its singularities. There is a definition of Gauss curve. F corresponds to an algebraic extension Kx over Kcp2, and its Gauss closure is denoted as H. Then H can correspond to a small surface called the Gauss curve of X. Later, in order to calculate the fundamental group of Gauss curve more easily, Moshton and Teicher defined an equivalent definition of Gauss curve as follows. That is, we consider the fiber product arising from a general position F. F is S into CP2, the same as above, of degree n. As this definition, a fiber product of n. Let the extended diagonal be this. The closure is called the Gauss curve and denoted by X Galois. You can see this definition may be complicated and so complicated. On the basis of the previous explanation, let me have a result in 2021. It is well known that the smallest possible degree of an irreducible non-degenerate surface X belongs to Cp n at 1 is n. Such surface is said to be a surface of minimal degree. We get our main theorem. This theorem was proved by Aran, Gong, and me. As follows, the Gauss curves of surface of minimal degree in Cp n at 1 are simply connected surfaces of general type for n is greater than or equal to 5. Next, we completely compute the fundamental groups of Gauss curves for the surface of minimal degree in Cp n at 1. And the main truths of this proof of the above theorem are degenerations and surface and Bridger group technology. This Bridger group technology is very important in our proof. Now, the last part related to open question. We give an open question. This question is, it is well known that the fundamental groups of most surfaces of general type are non-commutative, but it is not easy to find concrete examples of such surface. We can let AK be series of integral number whose limit are infinite. How to give a series of surface of degree AK whose fundamental groups of Gauss curves are all non-commutative? This is our open question, and in the following, I and my teacher will solution this question. In closing, I wish to express my great appreciation once again for inviting me to participate in this conference. Thank you for listening.
Thank you very much. Lia G. Thank you. Let us send the speaker. Thank you. Please, any questions, comments, remarks? Yes, please.
I have a question.
Please.
I want the speaker to say more about the open questions.
I think this question is very good because I want to answer you as follows. When the AK is bigger, it is I think will be very difficult to compute the fundamental group of the complements of the branch curve. This branch curve is very difficult to get. So its quotient will be also very difficult and not easy to determine whether it is an abelian group. So we can get this open question and may be difficult, but I believe I can solve it.
Thank you.
Thank you. Please, any other questions, comments?
Sorry, can I ask the question?
Okay.
My question is connected with the number of integer points and with the number which are in correspondence with the number of curves for the Del Pezzo surface. Can you say that it is equal or not?
Equal or not? You say, please wait me about this. I share my screen. You can please. This you said this question about this.
Yes, this question.
If in general, if we know degree x is equal to the number of -1 curves of the partial surface of degree 5, 6, 7, 8. This result can be proved by the same way in our talk. We can also get this result by direct compute. For example, the number of -1 curve of the partial surface of degree bar is 1, of degree 8 is 1.
Yes, okay, but this number 200, for example, 240, it is not the number of integer points. Yes, it is only the number of curves.
About integer sections and -1 curves. You said about this, yes. After because we below down the suitable -1 curves, we can find a one-to-one correspondence between the -1 curves and the integral sections of original fibration. So this -1 curves is seen as integral sections.
Okay, thank you.
It's my pleasure.
Thank you.